Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 2.8, Rates of Change and Differentiability.
Lesson 2, Other Notations for f' and Differentiability.
The next thing I'd like us to look at are just some other notations for f' of x. Calculus was developed in the 1600s. It was actually developed by two different mathematicians, Leibniz and Newton. We are both given credit for it because they developed it at more or less the same time and developed the ideas independently. But because they were developed independently by two different people from two different countries, we have different notations for the derivative, and those different notations are used in different settings. Sometimes one notation is more useful than another. So the notation that we've talked about so far for the derivative, if f of x equals, for example, x squared, the derivative, we use this notation f' of x for the derivative. And you might remember this was our very first example, and we went through the whole limit as h goes to 0 definition of f' of x, and we ended up finding after a long series of steps that f' of x was equal to 2x. Well, sometimes our original function is written differently. Instead of f of x equals x squared, sometimes it's written y is equal to x squared. And in that case, we might write y prime is equal to 2x. And y prime then is another notation that means exactly the same thing as f prime of x. So f prime of x and y prime mean exactly the same thing. When we start with a function f of x and we find f' of x, its derivative, we have a special verb for that process. It is called differentiating our function. So let me just write that in here. It is called differentiating because you're finding the derivative of differentiating our original function, our f of x. So if someone says find the derivative, they might also say differentiate the function f of x to find f' of x. One thing you might notice is that when we're given a function and we differentiate it, we find its derivative, we can think of that process as an operation that we perform on the original function f to get a new function, the derivative, f'. So we often say that differentiation is an operation. It's something that we do to f in order to get to f'. So we say it's an operation we perform on the original function f to get f'. So just kind of keep that in mind for this next notation that I'm going to show you. And I realize that it seems confusing at first when you have all of these different notations, but you will get used to them fairly quickly as all meaning the same thing. So since differentiation is an operation, we use what's called an operator notation. We'll see in a minute where this crazy looking notation comes from, but we use a notation that we say in words, d by dx. So let me write that in words. We say d, the letter d, by dx. And we write a d, it looks like a little fraction, over a dx. And I'm going to put some brackets here, and I'm going to put my original function inside those brackets. So f' of x can also be written this way as d by dx and then in brackets of my original function. And we think of this as an operator symbol kind of like a square root symbol. If you say square root of x, it says take whatever number x is and find its square root. D by dx says take whatever function is inside here and find its derivative. Differentiate the function that you find inside of the square brackets. So for example, if I write f of x equals x squared, if I have that particular example, and then I said, oh, I want you to find the derivative of f of x, that would mean find the derivative of the function x squared in this particular example, and the derivative of x squared is just 2x. So you can think of this little symbol here as meaning find the derivative of whatever ends up being inside the square brackets. Find the derivative of x squared, you go through the whole limit as h goes to 0 process, and you end up with the answer 2x. So those are a couple of new notations for the derivative y prime, if our original equation is written as a y instead of an f of x, or this operator notation, and this is just a symbol that means find the derivative of whatever function follows, whatever function is inside those square brackets. Well, let's go ahead and see if we can understand a little bit more where that weird looking symbol comes from. So that's what we're going to talk about next, is where did that weird d over dx symbol come from? And remember that what we said was f prime of x could be written as d by dx of f of x. Well, f of x is really exactly the same thing as y. And so sometimes instead of writing d by dx of f of x, we'll write d by dx of y, but traditionally it's never written this way. So we don't write it that way. We actually pull this y into the numerator and we write dy dx. And that's read dy over dx, or the derivative of a y with respect to x. And traditionally, this is the way that we actually write it if we're going to write it with a y instead of an f of x. Well, that may look even weirder to you, but there's a reason for this weird notation, and that sort of works backwards to a reason for this operator notation that we talked about on the previous page. So to understand where this weird notation comes from, we have to go back and remember that the slope of the tangent lines came from looking at a limiting sequence of secant lines and looking at their slopes. So you might remember that the slope of the secant line through 2 points on the graph of y equal f of x is found by just figuring out the change in the y values over the change in the x values. And so if you have some delta x here and some delta y here, the slope of this secant line is just delta y over delta x. It's the rise over the run of that secant line through 2 points on the curve. But remember, in order to get the tangent line, what we did was, if I wanted the tangent line at the point P, I took this point Q and I slid it down the black curve and got a sequence of secant lines. And those secant lines got closer and closer to what we intuitively think of as the tangent line. Well, think about what happens to this delta x as the Q slides down the curve towards P. It means this change in x here is going to get smaller and smaller. It's going to be approaching 0. And in the limit, you could think of the delta x as shrinking all the way down to 0. You might also notice that the delta y is also getting smaller and smaller. As I go from this point Q and I have some delta y that's this high, some rise, to another Q that's closer to P, and I have a new delta y that's only this high, the delta y's are actually also shrinking down towards 0. Well, f prime of x is the slope of the tangent line. We said it's the limit as h approaches 0. H is really the same thing as delta x. It's this difference in the x values along the secant line. So you could write it as the limit as delta x goes to 0 of the slopes of the secant lines. Or another way to write it is the limit as delta x goes to 0 of delta y over delta x. That's what we just got through saying the slope of the secant line is delta y over delta x, so I just plugged that in place of slope of the secant line. Well, this is just a little remark. Don't worry too much about it. It's just to give you a little bit of background. But notice that delta y over delta x, the delta begins with the letter D. And so when we do the limit as delta x shrinks all the way to 0 and go from the slopes of the secant lines to the slope of the tangent line, the delta y and the delta x become infinitesimally small. We have just, as q gets right on top of p, we have a tiny, tiny little change in the x values and a tiny, tiny little change in the y values. And so we say that symbolically, the delta y becomes an infinitesimally small change that we call dy, and the delta x becomes an infinitesimally small change in the x direction that we call dx. And so dy over dx is meant to remind you of where the slope of the tangent line came from. It came from the slopes of the secant lines, which are found by doing delta y over delta x. But once you do this limiting process, we say you go from the limit as delta x goes to 0. Once you do the limiting process, you go from a finite change in y over a finite change in x to an infinitesimally small change in y, denoted dy, over an infinitesimally small change in x, denoted dx. And that's where this weird notation comes from. Is it meant to remind you of the delta y over delta x that we use for the slope of the secant line? And because this is written as dy over dx, that's why if you sort of go through these steps backwards, you could think of it as d by dx of y, which is d by dx of f of x, and I believe that is how this operator notation got born. Okay, so that's just a side remark so you have some clue of where this strange notation comes from. But that means that if I have something like y equal x squared, one way to write the derivative would be y prime, and you can say, okay, y prime is equal to 2x, but here's another way to write the derivative. Y prime means exactly the same as dy dx, so that would also be equal to 2x. Now, let's also talk about how we use all of these different notations. We've actually talked about a number of them. We talked about the f prime of x notation. We talked about, we said that's exactly the same thing as y prime, which is exactly the same thing as the derivative with respect to x of f of x. That's our operator notation, which is exactly the same thing as dy over dx. That was the last notation that we talked about down here. So we have these four really different ways of writing the derivative at a general point x. Let's talk about how to write these different notations at a specific value of x, at a particular point corresponding to a specific x. For example, suppose I want my derivative not at x but at 3. How do I write that using the y prime notation? Usually we simply write y prime of 3, as if y were the name of the function. It's a little sloppy, but we often write it that way. If I want to do it using the operator notation, we usually do it in the following way. We say find the derivative with respect to x of f of x, and then we want to specify that we're going to evaluate that at the value x equal 3. Sometimes we put a vertical line here, or sometimes we just write down here in the corner x equal 3. Well, what does this weird thing mean? It means find the derivative of your function and then evaluate it at x equal 3. More commonly, you'll see it written this way: dy dx, that's the general derivative, and we draw a vertical line like this and write x equal 3 after it. So it's just a notation that came up. It looks rather complicated, but it says find the derivative, find dy dx, and then when you're done doing that, evaluate that derivative at the particular value x equal 3. Exactly the same meaning as what we have over here. F prime of 3 means find f prime of x and then plug in 3 in place of x. So it means the same thing. I'll just make one last remark about this dy dx notation. You might think, oh gosh, that seems so much clumsier than just writing f prime of x. But it does turn out that this notation, in a sense, keeps track of what input variable we're taking the derivative with respect to, whereas the f prime notation does not once we've filled in a particular value for x. So it turns out that the dy dx notation, because we have an x down here in the denominator, tells us very specifically that we're finding the instantaneous rate that this output variable y is changing with respect to the specific input variable x. And so it's a nice notation for a lot of applied problems. And we'll see later when we talk about related rate problems that it is a very nice notation for finding the rate of change of an output variable y with respect to an input variable x. So just kind of keep that in the back of your mind, and later on when we get into the next chapter, I'll make another remark about that again. Okay, let's go ahead and look at the next page. I'm going to skip this example that's down here at the bottom. Okay, so now you've seen several different notations for the derivative, and you will get used to using all these different kinds of notations. They all mean the same thing as f prime of x, but some are more useful in some situations than others, and you'll start to get a feel for that as you do more exercises in this chapter and the next. Okay, well, I'm moving to the next page, and notice that our next topic is differentiability of a function. What do we mean by that? Well, I'm going to explain that later on this page. But first, let's just think about a function y equal f of x and remember our definition of the derivative. We said f prime of x is the limit as h goes to 0 of this kind of complicated expression, f of x plus h minus f of x all divided by h. And you might remember that when we defined this derivative, f prime of x, we said it's equal to the limit of this expression provided that limit exists. And the question we're going to try to answer is, does this limit always exist for every function y equal f of x at every x? And it turns out, unfortunately, no, that limit does not always exist at every x value for every function. One thing I want you to notice in this limit expression is that h is approaching 0. It's an overall limit, so h is approaching 0 from both sides. H is approaching 0 from the right, and h is approaching 0 from the left. So keep that in mind. We'll use that in this next example. So here's an example of a function, and I'm just going to show you several examples in the next page or so that show places where a function might have a problem, where this limit might not exist. So we'll look at all the different places where a function might not have a derivative at a particular value of x. So my function here, you notice something kind of weird happens in this function. That's supposed to be continuous there. At x equal 8, there's this like sharp point in the curve, and such a point is referred to as a cusp. It's a place where the curve just comes up to a sharp point. And for this particular function, we'll see that there's a problem with trying to find f prime of x right at the value x equal 8. Notice that f prime of 8 would be the limit as h approaches 0 from both directions of f of 8 plus h minus f of 8 all divided by h. And I'm going to try to argue that the limit of this expression doesn't exist. Well, why would we have a problem? What I'd like you to do is first consider the limit of this expression as h approaches 0 from the right. And if h is approaching 0 from the right, remember that h is greater than 0. In other words, h is some positive value. So if you look at 8 plus h, you're taking 8 and adding something positive to it. think of that as your x value. So my x value, if h is something that's positive and I add h units onto 8, my x value is going to be on the right-hand side of 8. Well, what is the limit of this expression? The limit of this expression should be the slope of our tangent line. If we look at just this expression itself, it's really the slope of a secant line. But the limiting value of this expression is the slope of our tangent line. But what I'd like us to do is to think about what that tangent line is approaching as x gets closer and closer to 8 from the right-hand side. If I pick this particular x value and thought about the tangent line right there, I would have a tangent line slope that is something that's negative. As I move to the right, I fall along this particular line. So maybe this has a slope of -1, something like that. As x gets closer to 8, and I think about what's happening to the slopes of the tangent lines, it looks as if this slope is it's a steeper line, so it's an even larger number in absolute value. Maybe this is a slope of -2. And the closer I choose my x value, but staying to the right of 8, the steeper my tangent line is, and the bigger a negative number I'm getting out of this for the slope of the tangent line. When I get right on top of 8, it looks like a very steep line with a negative slope. Maybe the slope is -5, something like that. So it looks roughly like the slopes of the tangent lines as I let x come in towards 8 from the right side are approaching some fairly large in absolute value number, but negative. All right, now let's consider the limit as h approaches 0 from the left of this same expression, f of 8 plus h minus f of 8 all divided by h. Okay, h, remember, is approaching 0 from the left. That means h is less than 0. It's something that's negative. If I take 8 and I add a negative number onto it and think of that as my x value, notice that that will be something that's a little bit less than 8. So when I add something positive, x was something that was a little greater than 8, but when I add something negative to 8, I'm looking at an x value that is slightly less than 8. In other words, to the left of 8. So think of an x that's over here. Let me try to get a different pen color. That's to the left of 8. Go up to the curve. The limit of this expression should be getting closer and closer to the slope of the tangent line as x approaches 8 from the left now. And the slope of the tangent line at the point corresponding to this x, you notice, is actually a line that has a positive slope. Maybe it's a slope of +1. And if I pick an x value that's to the left of 8 but a little bit closer to 8, I'll get something that's even steeper for a tangent line, and maybe the slope of the tangent line there is a slope of 2. And as I let my x come right on top of the 8, just very slightly to the left, I'm going to get a tangent line that looks like something like this, and maybe the slope of this line is 4. So it looks like a fairly large positive slope, and so I'm going to say the slope of the tangent lines as I get closer and closer to 8 from the left look like they're going to be some positive value, such as 4. So this is not a careful proof, but hopefully it's an argument that if I look at the limit as h approaches 0 from the right of my expression, I'm getting the number -5 for that right-sided limit. If, on the other hand, I let h approach 0 from the left of this expression, I'm getting the number 4. That is the limit from the left of this expression. And what's the problem? The problem is for the overall limit to exist, and that's what we would want to exist to say that the derivative exists at 8. This overall limit only exists if what is true about the one-sided limits. This limit only exists if the left-hand limit and the right-hand limit are the same. In other words, if the one-sided limits exist and agree. So I'll say are equal. Well, are these one-sided limits equal? No. These one-sided limits are not equal to each other. The limit from the right is -5, the limit from the left is 4, and therefore the overall limit does not exist. So this particular function that has a cusp at 8 and has a different tangent line as we approach h from the right than it does as we approach from the left is a function that is not differentiable at x equal 8. This derivative f prime of 8 does not exist. Because we said the derivative at 8 exists if and only if this limit as h approaches 0 from both directions exists. Now, intuitively, we don't usually go through all of this for a cusp, but intuitively what we say, I'm going to redraw the graph up here. Here's 8, and I'll just draw a cusp here. Intuitively, what we say is that there's no unique tangent line right at x equal 8. If you thought about taking a ruler and trying to figure out, well, what direction should the ruler go right at that cusp point so that the line follows the curve as closely as possible, sometimes what we say is simply that there is no unique tangent line. You have this sharp point here, and the tangent line, there's no particular tangent line that I could pick that seems appropriate right at that point and would be something that would uniquely follow that curve more closely than any other line does. So intuitively we say no unique tangent line exists at 8. So no unique tangent line exists at x equal 8, and that will be true anytime you have a cusp, and so the function will not be differentiable at such a cusp point. Let me just define differentiability a little bit more formally. We say f prime of x exists at x equal a. If that's true, then we say the function is differentiable at x equal a. For the example we just looked at, f prime of 8 did not exist, so f prime of x didn't exist at 8. And so we would say this function is not differentiable at x equal 8. If the function isn't differentiable at x equals a, we say that if not, I'll put if f prime of x doesn't exist at a, at x equal a, then we say f is not differentiable or is non-differentiable at x equal a. So if it's not differentiable at a particular value, then we say it's not differentiable or non-differentiable at that particular value. Okay, so I'm just going to summarize what we've said over here. We've found some places where a function will have problems, where a function will fail to have a derivative. And whenever there is a cusp, as we looked at in the last example, or what's sometimes called a corner. A cusp is something like this that has sort of a peak like this with curves coming in, and a corner is something like this where you have straight lines on either side of the point. So whenever a graph has a cusp or a corner, f is not differentiable, or we could say is non-differentiable at that point. And what I'd like you to do is to pause the video for a moment and think about this example that's graphed here. This is our function y equal f of x, and pick out all the places where the function fails to be differentiable, where it is non-differentiable, and then we'll go ahead and do it together. So take a couple minutes and do that. Okay, so where does this one fail to be differentiable? Where is it non-differentiable? Well, the x values that have troubles are wherever we have a cusp or a corner. So notice at x equal 5, that we say there would be no unique tangent line. If you tried to draw a tangent line right at 5, you could draw all kinds of lines, and you really couldn't choose one of them that you would think of as the tangent line that would match the slope of the curve. Or another way people like to think is that the tangent line as you come in towards 5 from the left looks like a totally different slope than if you come in from the right. In fact, it looks, as in our previous example, like the slope is positive as you come towards 5 from the left, whereas the slope of the tangent line on the right side looks like it's something that is a positive value. So negative from the left and positive from the right. So x equal 5, there's a cusp, and so it is not differentiable there. At x equal 9, it does look like there is a sharp change in the tangent lines. So the tangent line as you come into 9 from the left side might look something like this, but as you approach 9 from the right, the tangent line looks more like this. So whenever there's a sharp change like that, it is not differentiable. The function f is not differentiable there. So at x equal 9, I guess we could call that a cusp again. There's a sharp change in the slopes of the tangent lines right at that point. And what about x equal 10? That's the other weird one. And yes, that's also a place where this function is not differentiable because we have a corner. You notice that the tangent lines coming in from the left side looks like a negative slope, whereas the tangent lines coming in from the right side has a positive slope. There's a sudden change in the slopes of the tangent lines because we have a corner right there. And so that would be a place where f is not differentiable. So we would say f is not differentiable, and I'm just going to abbreviate it, differentiable there, at these three x values, 5, 9, and 10. Okay, well, let's look at some other kinds of problems that come up in graphs of functions where a function would fail to be differentiable. So if you turn to the next page, here's a new function, y equal f of x. That's a nice kind of smooth function. There's no sharp change in the slope of the tangent line at any point. So you might think, oh, well, that should be okay. It looks like there's a unique tangent line at every point along that curve. And that's true. There are no sudden changes in the slope of the tangent line as we move along this curve. However, I would like you to think about what happens at x equal 5. Let's draw the tangent line at x equal 5, and there is a unique tangent line to the curve right at this point. But what line follows that curve the most closely right at x equal 5? Well, I've tried to draw the curve in a way that it appears to me that the tangent line would actually end up being a vertical line. So I'm going to say at x equal 5, it appears that the tangent line is vertical. Well, there is a unique tangent line. It just happens to be vertical, so that's fine. But what does that mean about the slope of the tangent line at x equal 5? What is the slope of a vertical line? Well, the slope of a horizontal line is 0, but the slope of a vertical line is undefined. So the slope of the tangent line right here, because it's vertical, is undefined. But remember that the slope of the tangent line at x equal 5 is the same thing as f prime of 5. And so what we're saying is that f prime of 5, which is that limit of that expression, limit as h goes to 0 of f of 5 plus h minus f of 5 all divided by h, that limit does not exist because f prime of 5 is something that is undefined. That's another way of saying that this limit of this expression does not exist. And so this function, although it's a nice smooth function with no sharp changes in the slopes of the tangent lines, this function is not differentiable at 5. I'll use my little shortcut symbol, the 3 dots in a triangle, meaning therefore f is not differentiable or is non-differentiable. It doesn't have a derivative at x equal 5. So now we found two types of places where a function will not be differentiable, where it won't have a derivative. At a corner or cusp where there's a sharp change in the tangent line, or anywhere where there is a vertical tangent line. So that's a new kind of problem that we have to look out for. Well, there's one other place where a function will fail to be differentiable that we're going to discuss, and that has to do with the graphs that are in the next example. So let's go ahead and see if we can look at, I have 4 different graphs, but we're going to collect all those together into one type of problem ultimately. But let's look at this graph first. This is a graph that's a nice smooth graph, except it's not continuous at 6. You notice that there is a hole in the graph at 6, and so this function fails to be continuous at 6. Well, if you said, gee, what's f prime of 6? Remember, that would be the limit as h goes to 0 of, and we replace the x's in our definition with 6, so I have f of 6 plus h minus f of 6 all divided by h. So we would be trying to find the limit of this expression. But there's a problem with this expression. Can you see what the problem is with this particular expression? Notice that one of the things in the numerator is f of 6, and what can you tell me about f of 6? If I try to plug 6 into this function and try to get the output value, I go up to my black graph, but I don't hit a point here. Remember, this circle means there's a hole in the graph, and we go right through the hole, and we never hit the black graph. In other words, f of 6 is undefined. Well, if a portion of our expression is undefined, then the whole expression is undefined, and that means the limit as h approaches 0 of this expression does not exist. And so f prime of 6 doesn't exist, and that means f fails to be differentiable at 6, and it's because we had a hole in the graph. If you think about the function that's graph to the right here, which I also called f of x, the same problem occurs. If you were to write out what f prime of 6 is for this function, you notice that if you tried to figure out what f of 6 is for this function, there is no point on the graph corresponding to 6. You're trying to go up and hit the black graph so you can go over to the y-axis, but you never hit it. Again, f of 6 is undefined for this function. Has a vertical asymptote right along the line x equals 6, excuse me. And so since f of 6 is undefined, it means this whole expression is undefined, and the limit then would not exist, and so f prime of 6 doesn't exist, and f would not be differentiable at 6. And that's because we have a vertical asymptote here, vertical asymptote. But notice that in both of these cases, my function wasn't continuous at 6. Here because there was a hole on the graph, and here because there was a vertical asymptote. So now let's look at a couple other ways that a function might fail to be continuous. Here I have a jump discontinuity at x equals 6, so there's a hole in the graph at 6, but the function is redefined up here, and you might think, well, hey, that should be better than the one that's right above it, because remember, the problem with the limit in the one that was above it was that f of 6 was undefined. And in this case, if I want to find f of 6, notice that it is defined. To find f of 6, I start out at 6 on the x-axis, I go up, I go right through the hole in the graph like I did here, but I do hit the black dot, and so when I go over to the y-axis, I do get an output value, and my output value is 5. So if I start to write out this limit, you might say, oh, that's fantastic. Now f of 6 is defined, and the value of this is equal to 5. However, I want you to think about what's happening to f of 6 plus h. As h approaches 0 from the right, 6 plus h is going to be approaching 6 from the right side. And as it gets closer and closer to 6 from the right side, it looks like the outputs are getting closer and closer to the number 4. And if I were to let h approach 0 from the left side, 6 plus h would approach 6 from the left, and the output values of f of 6 plus h would also be getting closer and closer to the number 4. So this thing is getting closer and closer to the number 4. That means that as h approaches 0, the numerator of my expression is approaching 4 minus 5, or negative 1. What's happening to the denominator, though? H is approaching 0, so this is getting very, very small, either small positive or small negative. So it's getting smaller and smaller, positive or negative. And we've talked about this kind of limit before. If the top of my fraction is getting closer and closer to some non-zero number, while the bottom is getting tinier and tinier, remember what happens to the overall function. The overall function, the overall fraction, I should say, is blowing up and approaching either positive or negative infinity. And it would approach actually positive infinity as h approaches 0 from the left side through negative values, or negative infinity as h approaches 0 through values from the right side of 0. But whichever, it doesn't really matter, because remember, when a limit is equal to infinity or negative infinity, that's really a special way of saying that this limit does not exist. And if this limit doesn't exist, it means f prime of 6 is undefined and the function is not differentiable at 6. So here was another type of discontinuity. This was what was referred to as a removable discontinuity, and it jumps up at one particular point. But all of the examples we've looked at so far are examples of functions that were not continuous at 6, and they turned out not to be differentiable at 6. The only other kind of discontinuity we talked about was this type. This is what we refer to as a jump discontinuity, and you can see that yes, this function fails to be continuous at 6. There's sort of this jump in the curve right at 6. And you can check in this case as well that the function fails to be differentiable. And it's the same type of situation as here. As you approach 6 from the right and as you approach 6 from the left, these values will be different values. As you approach from the right, f of x is getting closer and closer to 5. As you approach from the left, f of x is getting closer and closer to 3. And you're going to have the same kind of situation in the numerator of your limit expression. You're going to have something that's going to some fixed non-zero number in the top. The bottom will still be going to 0, and the overall limit will be going to either positive infinity or negative infinity. So it will be another case where the limit does not exist, in this case because the limit is blowing up in size. So I'll let you sort of think out the details of that one yourself, but all of these, notice, are places where our function is not continuous. And what we're noticing in all of these things is that if f is not continuous at x equals 6, then f prime of 6 is undefined. That limit does not exist. And so f is not differentiable at such a point. And that turns out to be true in general if the function is not continuous at a particular x value, then it is not differentiable at that x value. The limit as h goes to 0 of our expression, f of x plus h minus f of x divided by h, simply does not exist. Well, let's try to summarize what we've said so far. And so let's turn to the next page and summarize when f prime of x fails to exist, or is undefined is another way to say it, at a point x equal a. And it will fail to exist if, and the first thing we said is if there is a cusp or corner at x equal a. The second place we talked about is if there is a vertical tangent line. Vertical tangent line. So the tangent line exists, but unfortunately remember that the slope of the tangent line is undefined, and it's the slope of the tangent line that's equal to the derivative. So the derivative will be undefined. And the last one we talked about, we saw several different examples, but in general, whenever f is not continuous. So f prime of x fails to exist at a point A if any of these things happen on the graph of our original function f, the graph of f. So I'll say if the graph of f has a cusp or corner, has a vertical tangent line, or is not continuous at x equal a, then we're in trouble and f prime of a does not exist.